Thank you very much. Hello, everyone. My name is Olivia Kilday. I'm an undergraduate student at Southwestern University in Georgetown, Texas. It's a little bit north of Austin. And I did research with Dr. Jacob Schrum on text-guided diffusion models in Super Mario Brothers. So, with previous research into procedural content generation, there's a couple of different models and things that have been tried over the years. We have long short-term memory networks, models that are based off of repeating patterns that they've already seen, generative auto adversarial networks, variational autoencoders that deal mostly in searching latent spaces. And then more newly, after the recent AI explosion, you have things like the $5 model, which is a very lightweight, versatile network, large language models, obviously, and unconditional diffusion. These things have all been explored, many of them with Mario specifically. So these models have had a lot of limitations and a lot of successes in the field of procedural content generation, but they're not always perfect. For example, with long short-term memory networks, it's very hard to say, like, I want to have this thing at this point in the level. I want to have, in the example of Mario, I want to have a pipe later on, not necessarily at the start, because they just repeat based off of what is in the first little part of a level. You can combine latent inputs with evolutionary search or do Boolean conditioning, but these are very clunky methods of saying exactly what you want at any given time. With text guidance, you do get a little bit more open. For example, there was a model that was created based off of GPT-2 called Mario GPT that was trained on Mario levels that, was able to have some success where you could input a caption and give you a level. The $5 model also uses text guidance, albeit it's a little bit small, so it does have its weaknesses. And very recently, there was a paper that came out just this year about using text condition diffusion with game maps, more like dungeon style. And it does have a lot of similarities and carryovers with our paper, but we've done some stuff they didn't. So what have we done? We have a method to automatically generate captions for a given level and determine how well a model adhered to those captions. We have compared a bunch of different methods of encoding text and putting it into a diffusion model to see which one performed best. And we've also created a GUI in order to combine smaller level scenes into full Mario levels. So in order to train a diffusion model, you need a data set. We're going to be using the video game level corpus. I'm sure we're not the only people here that are going to be using that. We are combining data from Super Mario Brothers 1 and Super Mario Brothers 2. Super Mario Brothers 2, known here in North America as Super Mario Brothers The Lost Levels, not the Doki Doki whatever game that they reskinned into Mario. We did manually clean this data up a little bit. The link to that cleanup data is in the paper. We have a GitHub repo for it. After we have this data, we're going to slice it into level scenes. They're going to be 16 tiles wide, 16 tiles tall. And then we're going to be scanning for the presence or absence of various different things like, hey, is there a floor? Are there pipes? Are there coins? So on. Once we've looked for everything, we're going to make captions out of them. There's a couple different kinds of captions. We have 3 regular captions, kind of what you expect. If there's a floor, we say, hey, there's a floor. If there's coins, we say there's coins. 2 enemies, we say there's 2 enemies. It's pretty self-explanatory. With absence captions, we also specify everything that is not there. If there is not a pipe, we say, hey, guys, no pipe, and so on and so forth. Since we're using diffusion models, we also can have negative captions. So in those cases, we'll just take everything that we would have put in absence caption and just slot that into our negative captioning. And we're going to be trying all 3 of these versions of the model just to seeing, can we get any improvement with any of them? We have 3 different text embedding models, one of which we trained ourselves. It's a transformer model that we trained using mass language modeling, so we call it MLM. Mass language modeling is just where you essentially hide one of the words in a phrase and try to get the model to figure out what that word was, so it gets some semantic understanding of what these phrases look like and how they're related to each other. We also took 2 models off of Hugging Face that were built for, embedding sentences or documents. They both have very long names. One we call Mini-LM. It transforms sentences. It's designed to transport sentences into a vector that's 384 numbers long. GTE is designed to transform entire documents. It's a lot bigger of a model. It's designed to take documents and put them into a vector of size 1024. Both of these have been used for this kind of thing before, and we're just going to be, again, comparison. For mini-LM and GTE specifically, because they're not designed necessarily on this data set, we are going to be testing two different modes. One where we take the entire caption with all the different things and code that into one vector, and one where we encode every individual phrase. So if I say two enemies, that's its own vector. And then if I say one pipe, that's a vector. One staircase, that's a vector. So that's what single and multiple means. You'll see that later on. Once we have all that data, we're going to be putting into our diffusion model. This looks a little scary. It's not that bad. We have the original encoding from the VGLC over on the left. We're going to be integer encoding it and then using that to get our captions and then putting that into our different models to get embedding vectors. Once we do that, we are one-hot encoding those integers and then adding noise to them with a noise scheduler. Then that goes through several rounds of downsizing and upsizing while we give the model the caption just to give it a little helping hand. And the idea is by the end, we're going to train this model to tell us what of this noisy image, what of this noisy tensor is noise. So we can then remove it. The idea is towards the end, we can just give it a full set of noise and a caption, and it will be able to back solve a level that looks like stuff it's seen before. We're using two kinds of loss here, mean square error and reconstruction, and we're combining the two of these together. So in order to test how well our models have done outside of just the loss function, we're using our caption adherence. So the idea behind this is we take our original caption, and that's like this long phrase with a bunch of different elements, and we compare it to the caption that the model generates, or the caption for the level scene that the model generates. Then we can compare each of these caption phrases together to get a score, which we're going to be averaging. So take, for example, let's say we have, we say we want a level with two enemies in it. So two enemies is one of these little individual caption phrases. If what the model produces has two enemies, great, you get a score of 1. Congratulations, you did your job. If it has one enemy or 4 enemies or whatever, you get a score based off of how close you were to 1. If you don't have any enemies at all, -1. You failed your one job. We do have a special case specifically for things like the ceiling or the floor, because it's a little hard to quantify what we mean by closer to an amount of ceiling. So for those, if it doesn't get it exactly right, then we just give it a flat score of 0.1. Now, in terms of actually, graphing everything and seeing how well our models did, here's the caption adherence score on our test data set. So these are captions that were not trained on originally, but are real captions that appear in the original Super Mario Brothers game. And you can see all the models did quite well. We can see the $5 model there, the FDM, and see that it kind of tapers off. We only traded that for 100 epochs because it started to overfit a lot, and you'll see some of that evidence of that later, and more details of everything in the paper again. The MLM model, despite being the smallest, performed the best everywhere, which is very interesting. And yeah, we don't see that much of a benefit for absence or negative captions. Regular seems to do just as fine, if not better, on everything. Now, that's on our test set. That's real Mario captions. What about captions that aren't in Mario? We also generated a data set of random captions, which you can see here. The scores here are a lot lower. The maximum tends to be about 0.4 instead of 0.1, which isn't great, albeit that is somewhat expected. Some of these captions don't make a lot of sense. If I gave you a caption and said, hey, give me a staircase and 3 coins, where's the floor? I don't know. And so if the model gives you a floor, it's punished for that. But still, we do see some weakness in what the models are able to do here across the board. MLM still tends to do the best, albeit there is one peak from GTE multiple absence, which you can see there, although it comes down to earth with more training, which is interesting. The FEM models, you can start to see some of the evidence of overfitting because they actually decrease in performance over time on these random captions. So with how long these models took to train, some of them took a very long time. Here's the graph of all the different models we trained and how long they took, at least on average. The NLM models were the quickest of the diffusion models that we trained that were text conditions. You can see the $5 model there at the bottom where it says FDM mini LM, FDM GTE. Those bars basically aren't there. They're extremely quick to train, which is why they have weaknesses. But again, there's still some use there. We can also see with the GTE model specifically, it tended to take a very, very long time to train. The longest model that we trained was around 150 hours of training. It took a long time. We only trained one of those for that reason. Now, we also have the training time for the MLM model itself, like the text encoder, instead of the diffusion model with the text encoder. That took so little time to train that you can't even see it on there. That was a very fast training model, but it is on that graph and you can see it on the paper if you zoom in a little bit. And we also graphed the best time, which we, took to mean the time it took for the best caption adherence score, because we did not have any kind of, algorithm to say, hey, you're getting worse over time, let's stop here. We did not have early stopping. Now we have one more metric outside of training time, and that's level diversity. We're using average minimum edit distance, which you can effectively think of as just how novel are these levels. We have a couple different metrics. The red and orange bar that you see on all of those are comparing against real captions that appeared in Mario. There's not a lot of diversity between the levels that the models created and real Mario levels when you give them captions that appear in Mario. This is a good thing. We don't want there to be a lot of diversity. When we give them captions that appear in Mario, we want it to look like it's from Mario. With random captions, we do see a lot more diversity, which is also a good thing. Things with weird captions get weird results. Again, we do see that decrease in quality. You can see in that rightmost image there where there's like some holes next to the pipe that shouldn't really be there, but we do get more diverse levels, which is good. This is the one time here in this presentation that we do mention Mario GPT in terms of actual metrics, because Mario GPT didn't work very well with our captioning data set. Its captions are a lot more simplistic and harder to work with in terms of I want these specific elements kind of thing. But Mario GPT is there, and it slots in pretty close between our random captions and our real captions, which is, solid. Now, in terms of what we've been able to do here, text-to-level diffusion is very possible, at least with limited caption vocabulary. Interestingly, the smallest model we had, the MLM text encoder with regular captions, performed the best. Generally speaking, the models that were bigger did worse. And that's not necessarily what you'd expect, especially given the current AI landscape where it's just scale, 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 scale with no other considerations. But it is one of those things where if you are narrow in your focus and you train something for a specific task, it can outperform other things, even if it's smaller. A couple other notes here that are just interesting. Pipes were mostly correct. They tended to look like pipes, but sometimes like a top left corner would be missing, especially on a random data set. That was very uncommon for real captions. But for random captions, it tended to happen more. It's one of those cases where models working less in their comfort zone tended to freak out a little bit and make mistakes they wouldn't ordinarily make. Our levels were mostly beatable. You can read about like those metrics in the paper, but it's pretty similar across the board. And one limitation of these models is that they're only trained to make very small levels. Of course, these models, you can give them a tensor of any size to randomly back solve into a level, but they're only trained on small levels. And so anything larger, the performance suffers a little. So in order to compensate with that, we've created a GUI, which allows a human user to construct larger levels directly from the model. So you can give it inputs and then say, hey, I like this little level scene, I like this little level scene, construct it into a little level, and then you could play it yourself, have A-star play it, and do all that, and then save it externally. So for future work, we're hoping to incorporate games with a little less data like Load Runner or with winding paths in Mega Man, or overhead perspectives and dungeon style things like the original Legend of Zelda. These are all things we've sent feelers towards, but don't have anything necessarily concrete for. We're also hoping to find ways to get better caption adherence on captions that didn't originally appear in this data set, because the performance still suffered more than we would like, even though that is a little expected given how weird some of them are. We're hoping to be able to generate larger models directly instead of having to use a human and a GUI to construct these things, and have a bit of a more flexible vocabulary, because right now it is a little bit limited and it does have to be programmed on a per game basis by a human user. You do have to have some knowledge of a game in order to use this. Thank you very much to the Southwestern University Research Fund for funding this. All the code, Hugging Face models, images, video, paper, everything that's going to be on that QR code right there. And then if you have any questions, not right now, not during this conference, you can email Dr. Schrum about them. But yeah, otherwise, I'm open to questions. We have like a Java-based emulator like baked right into the code in order to be able to play it. So like the GUI does let you play the levels directly, but it's just like a Java recreation of the original Mario one that's pretty accurate. Yeah. Was beatability something that was in the creation process? Like, was it created? It was not trained to make beatable levels. It was trained to make levels that looked like the original levels, which happened to largely be beatable. There's a couple exceptions with the lost levels, because there's some level scenes that are just empty, and then we have a wall here because there's like a wind effects and stuff in that game. Lost levels is weird. But these levels were just trained on the original things. All we were training these models on was the loss function and nothing else. We didn't train on caption adherence or anything. Those are all side effects we used to evaluate how effective the models were. Is there anything that for those that have big type No, so the way the $5 model works, at least from my understanding, is just like, hey, you give it this screen that's trying to recreate that. While Mario is, goes across, the level samples that we're like creating are just here's 16 by 16. We don't necessarily have information about what's beyond that. So the $5 model was able to learn based off of just what it saw in front of it.